Okay, great. So welcome back to the 4 Methods for Software Engineering lecture. And we started looking at Alloy, which is some tool for relational first-order logic. And we started looking at the language, some examples, what we can do. And then we said there is this tool that allows us to find some instances and some example instances of our models. And that's this Alloy analyzer. And this is the structure, how it works. So this is what we looked at the last time. And the reason we can use this is to enumerate finite scenarios. So the idea is, well, it has to be finite because we're using a SAT solver, and it's basically checking for some solutions within some bound, and this makes everything finite. So what we can do with this, with generating those kind of solutions, is we can validate a software design by looking at some examples that we could instantiate from this software. So we had this example with the linked list, and then we saw that we could generate some examples of linked lists, and we could see whether these are maybe good examples or bad examples. And then we can change our specification to maybe constrain it so that some bad examples don't appear in the scenarios that we want to see. We can then use this also to systematically test our implementations. So if we generate a scenario, we can check whether this also works in the implementation. This is like a test case generator, for example, and we can also use it to maybe check the reliability of those systems. We can look for some cases where things might break and see if they are possible. And if they are possible, we can try to figure out which constraints can we add to prevent them from happening. There are also some people who have used it for synthesis, for security analysis of hardware or other analysis of security protocols. So I think some telephone switches they analyzed with Alloy, and they figured out that there were some bugs in the hardware of the switch. And there are also some other security protocols. I think some HTTPS variants where they analyzed whether man-in-the-middle attacks are possible, things like that. Now, how do we make this work? Because we can probably, if we have one solution, we can probably maybe find another solution which is very similar. So the effectiveness of this approach, the testing, the validation, this really relies on maybe the diversity or the quality of the solutions, right? If they are all really bad solutions or all very similar solutions, they might not be so helpful. So too many similar ones, and this might lead to redundancy, which we do not really want. So we have to figure out a way to control this. And one way that is already implemented in Alloy is to have this symmetry breaking. So basically solutions that are just different based on some variables, but they basically look the same. It tries to automatically remove them. And here are some scenarios if we would generate them, but of course we can also use the this web interface to generate them. So we have here this exactly the same specification that we used before, which had those kind of two different constraints. We either have, for a cyclicity, we either have no list header, or there exists some element in the list where this is basically an element from the list, because we go to the header and then we go to all the things that are linked, and we say this doesn't have a further link. So the list must end somewhere, and then there's no cycle, because a list with a cycle would not end. So and then we saw some examples, stuff like this, which would be probably a good example. Which might not be a good example, right? So this is not really an example we want to see of our list. We have some node linked to itself. So we said, well, we can extend this with further specifications. So we can, for example, add, probably not in this. We could add this fact, all nodes in list, and then we could say something like, this basically is the set of all the nodes that we are looking for, and we can say node is in this. So this is like a set containment, because node, basically that's our signature, which means that in any instance, node will be a set of atoms, and we say this set of atoms is contained in this set of atoms. So we can say containment, or we can even say it equals. So because anyways, there can't be anything linked other than nodes, right? Link only goes to nodes, so we could even say equality here, and then we should only get interesting lists. So we just saw this empty list, which is also a very good test case. And then this list, for example, and this list. And that's already it. So now we have some very meaningful examples. We have an empty list. We have the one with 1, 2, and 3 nodes. So we can use this to enumerate the different scenarios. Here are some other examples with those dangling nodes that we just removed with our fact. And now we could translate these nodes into test cases and then test our implementation of linked lists. So if we want, what we're actually doing here is we're asking the analyzer in this specific run command. So we have those signatures and we have predicates, but they usually don't mean anything unless we put them in a run command. So there's an implicit run command, which just runs no predicate. That's usually the default implementation in Alloy. This doesn't work in the web front end here because this just checks, do you have a run command? If you don't have a run command, it doesn't activate the run button. So, how come? Okay, it allows us. Okay, so this would be the default. And you see this default here doesn't have the acyclic. So we have a cycle. So the default run command basically just runs everything. It takes facts into consideration, but not predicates. Because predicates are something that we say we need to tell it how to apply the predicate, whereas facts are something that we say we always want this to hold. Okay, so the run command is the really important ingredient of any analysis. We want to run the acyclic predicate for 3, which means that we want to find instances that satisfy this predicate, and they can be up to size 3 for each of the signatures. So the way that this is implemented is by using SAT solvers. And you can imagine if we are limiting the number of, well, what are we limiting here by this 3? That's the number of elements in the list, but this is limited to 1 anyways. And we're limiting the number of nodes, but so this will be then 3. So then there are only finitely many combinations of those, and Alloy will just try to use a SAT solver to find those that satisfy the predicate. So the run command is the important element to find scenarios, and scenarios, they're basically some satisfying assignments to the relations, and also the relations, this is basically the set of signatures and their fields. So these are all relations. And then we can look for multiple scenarios. We saw how to, kind of do this manually. Did anybody ever try to explore scenarios? I think we did it once for the feature model analysis, where we basically said, we now want to get a different solution, which we have not seen before. So we basically negated a product, and then we said, now give us a next one, and then this next one had to be different from the previous one we found. And this is exactly how Alloy works. It basically says, now give me a solution which is different from the one that I've seen before. Internally, Alloy, this high-level language, gets translated to, well, there are a few more steps. There's like another tool that runs in the background that's called cod, which is relational logic, but without some of Alloy's features. So it's first boiled down to cod, and then cod translates it to some negation normal form, which is translated to SAT, and then the SAT solver finds an assignment, and this is translated back to one of those scenarios. So, and the way that this works, that we can translate it to SAT, means we need to get some bounds, and these bounds are also called scopes. So there's this scope that we saw right here, this 4.3. This is defining our scope. And if we change this, let's say to 410, then we're going to get some possibility of longer lists, because now, yeah, is this already? Yeah, well, we would step through all of them. Maybe this is quite a long one. Now it's so long that we don't even see those links anymore, but they are still there. Yeah, so these are all still linked. They have to be, because we have this fact here. If we wouldn't have this fact, things would get very complicated. We would have many more instances, because then we could have nodes floating around wherever they want to float around. Yeah, we could have stuff like this, which is, yeah, maybe not the nicest list as you would imagine. It's just an empty list and then some nodes going crazy, right? But yeah, let's add this. So now it's a SAT solver, right? If we click run, you observe quite some, well, you observe some delay, right? Maybe there was a second or so. If we do only 3, much faster. If we do 10, it gets slower. If we do 100, well, how do SAT solvers work? Their complexity is in the worst case exponential, right? So by just multiplying it with a factor of 10, now we have not 2 to the 10, but maybe 2 to the 100, which is a very rough estimate, right? It's usually better than that, because it's not really 2 to the something in the SAT solvers. That's only in the worst case. Yeah, but we see we can't really handle large models. I think that's partially because we use this. So there are some features. Sometimes Alloy can easily go to scopes of 100, but there are some features like this here, this closure, where we say, well, apply all the combinations of this relation, and we will see exactly what this means. And this leads to timeouts. So this one is actually running on our server. So there is a limit of how many instances we can run. So if all of you are running some very big instances at the same time, then it will give you some message saying you have to wait a bit. So I think there's like, I'm not sure how many concurrent ones we have, but this, might happen. Limbool was running in your browser, so there doesn't matter how many do it concurrently, but this one, Alloy, this might have some performance issues if you run too many of them. Okay. And now it's stuck. Now our server is down. Let's see. No, okay. The server is still running. Good. Okay. Yeah, sometimes you have to just refresh the page, but we're working on that. We're trying to improve it. Okay, so the default scope usually is 3. How come? How come so small? There is this idea of the small scope hypothesis. So this hypothesis about the small scope says that if your software has bugs, then you can try to find, then these bugs will already exist in small scopes. So if there are any issues, you'll probably be able to observe them on small examples. This is, some kind of idea, which is quite common. So in software testing, in unit testing, you usually do some kind of boundary analysis. So you're not really testing exhaustively all possible values. You're just testing around the bounds because you think that that's where the errors probably exist. So that's kind of, decreasing the scope a lot. Then in combinatorial testing, this is, if you had software engineering with me, this was this in parameter order algorithm where you're trying to find the interactions of some subset of the parameters to get with some higher probability to observe a failure. So the idea here was that if you have an interaction of 2 parameters or 3 parameters and you cover those exhaustively, then you find maybe 70 or 80% of the bugs in the software. Then, of course, in mutation testing, you're trying to mutate the code to see whether your test cases find it. And of course, these mutations, they're also quite small. So everything we're doing is we're expecting that we can find bugs on some very small subset or some small examples. And we will also maybe see some examples where larger yeah, where larger examples are already quite difficult to even look at. So I think we had this one in the beginning that we used to motivate, where we had this one. Is this implemented? Let's see. Oh no, this was the previous version. Did we have a solution? Yeah. Our assignment example. And yeah, we saw that if we run for the default scope 3, that's already a lot. Let's do this maybe for 10. Then we can see we get very large instances, right? So an instance like this, you can't really see what's the problem or what's even the meaning of this instance. So the small scope hopefully helps you to better understand, better understand the instances. Yeah. Okay, but the small scope hypothesis basically says that if there is some kind of bug in the software, then hopefully we can find it by testing a small part of the program. Also, like SAT solvers, Alloy has the guarantee that it is complete. So it can always decide whether some property is true or false. Was this the case for SMT solvers? So SMT solvers sometimes could tell you unknown because the theories that we use, the logic itself is undecidable, and some theories they exhibit this undecidability. So sometimes in SMT solving you get this unknown. In Alloy you wouldn't really get the unknown, but that's only because we are running it on this bounded scope. So on this bounded scope, it is complete. And if there is an issue, it will find it. So if we find a scenario, we know that the formula is consistent. On the other hand, if we do not find a scenario, we don't know. So we kind of have this, it's complete, but only with respect to the scope. And then if it says, well, I can't find an example with, let's say, scope 3, it could be that there is an example with scope 5, but we don't know yet. So we would have to try larger scopes if we really want to find an example. Because in general, again, the logic of Alloy without the bounds is undecidable. And with the bounds, it becomes decidable because with the bounds, we can use a SAT solver and this will give us a yes or no answer. So due to the bounds, we're making this problem decidable. Okay. Then what are the main elements of Alloy? We already saw signatures and relations, and then we saw that we actually need predicates and functions. Well, we haven't really seen functions. We will see functions a bit later, but we saw predicates and we already saw facts. So the difference between the predicates and the facts, where that the predicate is something that we can state if we want to, but facts, they will always have to hold. And this idea of the run commands, so we could have multiple run commands. We could have another one. We could have a predicate called empty list. I don't know, for 3. Doesn't really matter. And then we can decide which ones are we going to run. Are we going to run acyclic or are we going to run empty list? Of course, now if we say run empty list, it's going to tell us that there's some problem with our model because this empty list predicate can't be found, right? So we need to, of course, say what this empty list predicate is. Now let's define this predicate empty list. For this, I want to see whether there is an empty list. Does the empty list exist? Because we saw that we had, I think, some issues here where then an empty list could no longer exist. So let's see if we can state empty list. How would I specify that the list is empty? Now we don't see the list signature. So here is our list, and it's only one list to make it a bit simpler. How would we specify that this is empty? What does it have to look like when it's empty? No header, yes. It needs basically to this, the header needs to be null, or we have no header. So, and this is exactly no list dot header. We would say what this actually means, this no, means that there is no element in this set. How come this is a set? List.header, why is that a set? And we're basically saying it's an empty set by saying no element in this. Why is list? So list is a set, right? Because list is the set of atoms. At the time that we interpret this model, list is a set of atoms which represent lists. What is header? Sorry? Header is relating list and node, right? So header is a relation. Header is a binary relation. On the left side of header, we always have a list atom, and on the right side, we always have a node atom. So we're now saying list.header. So we basically take the list, we navigate to the header of that list, and if we navigate from the list to nodes, then this lone says it's 0 or 1 nodes that we can navigate to. So basically now we are left with a set of 0 or 1 nodes. And if we say this list, this set is empty, that's basically what we're expressing here. Then we're basically saying this thing doesn't point to any node. So it points to 0 nodes, and that's what we're expressing here. So let's try to run this predicate. So if we want to have different run commands, we have to say which one we want to run. So let's run the empty list one. It found an example. How many scenarios will it find for empty list? Can I click next? Well, I can click next, but will it find anything? No, because there's only one way we can create an empty list. We need exactly one list atom. That's the one here. And then this list atom cannot have any header. So yeah, there's no other way to create this. What if this fact didn't exist? Can we still have empty lists? Yes, we can have empty lists, but now again, we didn't really say what we want to hold about the nodes, right? We didn't restrict the nodes to only exist in lists. So that's why we might have now multiple instances, but we can still check this predicate. So if later somebody decides to remove this fact, we still have this predicate as like a sanity check that we can still create empty lists. Okay, so if I put this back, and let's say I change this to one node. I say the list always needs a header node. Then suddenly my empty list predicate will no longer be satisfiable. It says no instance found. So this run empty list may be inconsistent. It's probably, it doesn't really know if it's inconsistent because of the scope. If we look at this and we say, well, if you can't create an empty list with 3 atoms, you will not be able to create one with 20 atoms, right? So for us, we know, yes, really, we cannot create empty lists anymore. Okay, so let's put it back to having empty lists. Okay. So yeah, that's about the different elements, facts, and different predicates, and we can have multiple run commands, and we could have multiple scopes. So we could have some run commands that only differ maybe in the number of scopes. Now, when I said that these things like list, that's a set, we will now look a little bit deeper into what do these things really look like. So here, the one that is highlighted is this one, the list with a single node. Then the signature list is a set of list atoms, right? And there's only one list atom, so that's called L0. The names of these atoms, they are usually based on the name of the signature attached with some number. Now the set node also has one element, right? Because there's only one kind of instance of node. And then we have the header. Now the header is a relation that associates a list with a node. And what about the relation links? What kind of relation is link? So here we see an example, right? For link, we see an example for link. So what does link do? Link associates two nodes, right? So that's also a binary relation that always has pairs of nodes that it connects. But here in this instance, what is the value of our set link? It's empty because, well, there's no, this relation basically is empty. There's nothing related here. Okay. Now, in this example, where we basically add one link, we would see a difference. The set of atoms now changed because now we have two instances of node, right? So the set node now has two elements. And suddenly we see that also the set link, which is this binary relation of links, has two elements. Sorry, it actually has a single element. So that's a single element. This arrow means that these are the two that are connected. So sometimes when you write in other notations, you write the round parentheses with a comma for the tuples, right? So here it's this kind of arrow to connect the tuples. Okay. Then this one doesn't highlight anyone. So which one is this? Which instance might this describe? E, yes, exactly, because we still have one list, but we have three nodes. So this must be, well, the only instance with three nodes is this. Let's check the relations. List is related to the node 0. And then it says here node 0 is related to node 1. Yep, that's this one. And then node 1 is related to node 2. That's that arrow. Okay, so that's the kind of the semantics or the meaning of these signatures and fields. So signatures are basically a set of atoms, and fields are a set of tuples that are combinations of atoms. And sometimes we want to further restrict them. So there are some multiplicities that we can use. For example, for signatures, we have some name, and we can put signature. We can put multiplicities in front of the signatures. There are the multiplicities 1, lone, sum, and set. 1 means exactly 1. We already used that one, right? We used it for the list. We said there must be exactly one atom in this signature list. Then there's also lone, where we can have optional ones. And there is sum, which means at least one. And there is set, which means it's unrestricted, could be any number. Then we can further modify. It's like in classes, you can modify signatures to say they're abstract. If you make, we already had this. So here we had an abstract signature person, which means that this person, there's nothing which is just person. So if we run this, we can only have, well, students and professors, but we can never have a person, because like a pure person, which is neither student nor professor, because that's an abstract signature. And then we can have this extends, which is basically inheritance. So you will inherit everything that person has. If person had a relation to other persons, then this would have been inherited. So how would we make a relation to other persons? Let's say we want to say that this person has friends. We would have to do it with a field, right? So the field, we could call it, well, friends. And then we have to give some multiplicity. So let's say set and then person. Now, if we run this, then, well, yeah, professors might have friends. Only professors? No. Really? Where are all the students gone? Hmm. How many times do I have to click to find a student? They all stayed home because of the weather? No. Really? Okay, so let's say for 3, but exactly 1 professor. So let's restrict the professors to not be more than 1. Okay, now suddenly we have also students. I don't know why it prefers professors so much. Okay, yeah. Okay, so now you can have these relations inherited. So that's basically this extends like you have in object-oriented programming. And those are, yeah, some further keywords. And then there's also disjoint, which is a bit tricky. That's allowed for relations where then you cannot have any same elements related to each other. We will see, I think, an example of this in, for example, quantification. If you want to quantify over elements, you often say that the 2 elements that you quantify over are not the same, so they are disjoint. Yeah, and we'll see some examples about these. And then we can have those relations which are declared inside the signatures. They can have exactly the same kind of multiplicities. So here, we had this a set of friends. Now we could say, well, it could be 1 friend, but it doesn't have to be, right? So now, yeah, this professor doesn't have any friends. That's allowed. You could also say some person. What does it mean now? It means at least 1, yes. So, and if we now want to, yeah, okay. So now we would have everyone needs to have at least 1, right? Because this sum is a multiplicity that applies to each person. Each person must have at least 1 other person in this relation friend. Okay. This inheritance, we just saw it with the, we already saw it here with the person, and then professor and student are inheriting, right? This is just a visualization. What it means is that if we have this class A, then the signature A, then the sub-signatures, they are basically contained in that set. So we had the person, and then students and professors are inside this set person. So all students and all professors are also persons. That's why we could define friends as other persons, and then it could be either a professor or a student, right? One thing that is important here is that the extensions of the same of the same signature, they're mutually disjoint. So this means that there is no element here which is A1 and at the same time A2. So if we have person and it's extended by professor and by student, then the person is either a student or a professor, but not professor and student at the same time in this model of inheritance. But that's exactly, I think, what we usually have in programming languages like like Java, where you can't have multiple inheritance. Otherwise, you have this, like in C++, sometimes this diamond problem, it's called, because you could have something that is in both sets, and that's usually tricky. So here we are disjoint. So 2 extensions of the same signature, they will never share an atom. Okay, and then we can, of course, make this super signature abstract so that it can't have any instances. So that's, yeah, exactly what we had before. And then this actually means we can actually do a predicate check, well, or we could say no, let's say no regular person. And what we want to state here is that person equals professor plus student. Now let's do a run command for this, run no regular person, and then let's run this. So now what we would get is we would make sure that the set person always consists of the union of the set professor and the set student, right? That's what we're saying. Now we get examples of where this is true, where every person is either a professor or a student. And we can go through them and we can see if there's any violation, but of course we know there won't be any violation, right? So what if we want to check that this predicate is valid in this model? Right now we're just checking satisfiability, right? We are putting it in a run command and we're getting an example where it is satisfied. But if we would really be interested in not only whether it's satisfiable, but whether it's also valid, whether it's not possible to violate it, right? So how would we check this? We always had this with SAT, right? We had in Nimbool, we could simply click, now I don't want to check satisfiability, I want to check validity. But then we saw that we can also do this validity check by using this semantic entailment, and we can do some tricks there. So how would we, yeah, we can negate it. So let's try to negate it. Now, well, we haven't really seen how to negate stuff, so let's put it in parentheses, and it's not very surprising. This thing is a Boolean expression, right? That's either true or false. So we can try to negate it just by saying not. Okay. Now, it doesn't find any, well, instance that satisfies the negation, which means that the negation is unsat, so the property was valid. So we've showed validity of this. Now, what if I remove this abstract here? Does it change anything? Now, person is no longer abstract. So maybe we can have a person who is not a student and not a professor. Let's see if our no regular person is still valid. And now we get an instance. So now we have a counterexample to our no regular person, because now we see a regular person. Okay, so that means that our validity check kind of works. Now we have a counterexample for our check that we just ran. Okay. Okay. Yeah, and we can also have another thing that's called subset signatures. So there's these regular signatures that are extending, and then there is this A3 in A, which means that any of the elements that are in A, they could also be in A3. And this is, yeah, a bit tricky. So we could have a signature staff in person. Now, if we run this, then some persons, they are identified as staff. So here, a student is staff. We can then, of course, also say effects that all the professors, their stuff. And then we can see that this actually now is this subset signature with the in. This can have both students and professors inside it. And so these are kind of two different ways of not really, yeah, well, kind of inheritance. I did, well, some analysis how often this in is really used. And there are one or two examples where this in is used. In the majority, you have this extends. So this extends is much, much more common than the in. But sometimes the in is also helpful because it doesn't matter what the concrete types are. You can still like select a subset from the set that you are here, well, subsetting with this in. So sometimes it's useful. Okay, yeah, and that's basically how it could be visualized. It could be like taking anything from our person, from student, from from professor. That's all possible. Okay, then about the multiplicities, we could define abstract signatures. Then their multiplicity is their like pure multiplicity would be 0, but of course, the multiplicity is always calculated for also all the subsignatures. So if I say I want 3 persons, then or 3 colors, then I could get well, red, yellow, green, for example, but not I don't know, red, yellow, green, because this would already be 4. If I don't want red to appear twice, then I could simply say 1 sig. Then this means that all of them, they can have exactly 1 instance. So yeah, in the first one, if I had scope 5, I could have colors like this, right? I can instantiate red as many times as I want. But here in the second one, I can instantiate each exactly once, and I have to instantiate each exactly once. So here I could have some color not even appearing. Yeah. So this would be the multiplicities for signatures, but then let's look at multiplicities for fields. So we have already used this, right? We have this lone multiplicity that we used for the header, that we used for the next node. Did we call it next? Where's our list? Well, link. We called it link. Okay. And they all had the multiplicity lone. Now, what does this multiplicity mean in terms of the elements? So we said it's a binary relation that links stuff from S to stuff from T. S and T are signatures, so they're atoms, right? So these, let's say these 4 atoms are in S, these 4 atoms are in T, and so on. And then the question is, which one of these actually respect the lone signature? Lone means that each element, each element, so F maps at most to 1 value in T. So each element in S has at most 1 value in T that it is mapped to. And we can make this slightly interactive. So yeah, here's the question. Which instances this A, B, C, D represent actually this multiplicity with the lone? So you can imagine S might be our list and T might be our nodes, and then we would have the list that has at most 1 header node. So our field F could be the header thing. Okay, we have three answers, and they all agree. So they all basically distributed their answers between A and C. So A and C are correct. Why? Yeah, maximum 1. So here S is, well, to T1. So here it's exactly 1, actually, right? So here each element from S is mapped to exactly one element from T1. Here we are violating it because S4 is actually mapped to 2. So this would mean that our list would have two header nodes, which is, yeah, not really possible. Here it is mapped, each one is mapped to 0, which is fine. So we could have our 4 lists and they all don't have any header associated. And here again, we have this violation where S2 is mapped again to 2 nodes. Okay, so yeah, these two, A and C, are correct. And this is how you would represent this in this alloy writing. So you would say S1 and T1 are a tuple that is in this set F. Yeah, so you would write these with each tuple with this arrow and then comma separated. And here, of course, what would be the set F for this second one? For this one? It will be empty. Yes, there are no tuples there. The set F here would simply be empty. Okay, so, and this means then, yeah, back in our example, stuff like this could be generated, but stuff like this, where a list has two headers, this definitely is ruled out by the multiplicity that we put. Okay, now, what if we change it to 1? Should we just go over them? So who thinks that the first one is representing this multiplicity 1? So this means that each element from the left is mapped to exactly one element on the right. Yeah. Who thinks it's not the case? I mean, we can just count, right? This one is mapped to 1, this mapped to 1, this map. They're all mapped to 1. So this one satisfies the multiplicity 1. This one here doesn't, for the same reason as it didn't before, because this is actually for 2. This one here, no, now it doesn't, because it needs to be exactly 1. So 1 means always exactly 1, so that also is not good. And this one, again, like in the previous case, S2 is mapped to 2 elements, so yeah, again, not possible. So now it's only the first one. That's fine. And yeah, this way we would generate something where definitely, let's say, each node we could have an element. So each node must have exactly one element. And then we would not have two elements in a node. Or no element, that's also not possible. Now set. Does this one reflect the multiplicity set? So set means we don't care how many are associated. Yes. So this one does, this one does, this one does, this one does. Yeah, they all do, right? Because if we don't care how many are associated, then all of them will satisfy this. So yes, all of them are satisfying this set multiplicity. And we might have something like, well, nodes with edges to a set of nodes, but then we no longer have a list. We would have something like a tree maybe, or even some stuff with probably cycles, right? I would guess that we can have cycles. But this behavior couldn't be generated. Why not? So the one on the right where we have actually two edges going from n0 to n1. Sorry? It could go the other way around. Yes, it could go from n1 to n0, but you cannot have two edges going in the same direction in the same relation, because the relations, they're always sets of tuples. So this means they can contain every tuple only once, right? So what tuple would this be? This would be n0 points to n1. And this one would also be n0 points to n1, but if you put them in the same set, they're only in there once, right? So a set, you cannot have these kind of double edges in any relation in alloy. You can't have this. Okay. Yeah. Then sum. Sum is now a different relation where it says maps to any number of values in this other set except for 0. So basically at least one. At least one, but then any number is fine. So which one? This one maps to exactly 1, so that's fine, right? This one, here we have the map to 2, that's fine, but S3 is not mapped to anything. So that's violating this sum constraint. Okay, so this one is not fine. Then this one, yeah, not fine because none of them actually has an element. This one, all of them have at least one element, so that's also fine. So here we would basically, this one should also be grayed out. It's not grayed out. Well, it should be grayed out. Let's grayed out. Okay. Yeah, now it's grayed out. Okay. And this would, for example, generate stuff like this, where we would have at least one or maybe more, but we couldn't have none. So, yeah. Now, the elements that we had for our list, they were quite, well, simple. We said the list can be empty. In non-empty lists, they only have, well, a non-empty list has exactly one header node, so that's why we translated it to this lone. It's either 0, which is the none, or, well, 1 lone. And the list should not contain any cycles. This was a bit more tricky with the cycles. And the node behavior, each node points to another node or points to null. Again, we translated this to the lone. So whenever you have some kind of data structure or some element you want to implement in Alloy, the first thing that you should do is you should check which of these constraints can you actually implement with multiplicities. Because that seems to be, in terms of the performance, that's one of the cheapest ways to implement it. Things like we did for the cycles, this was really expensive, as we saw with the SAT solver. But if we only have these kind of built-in multiplicities, that's always the best way. There are other ways to do it. So if we look back at our list example, so let's have one of the lists, this list here, and let's say go back to running it for 3. We don't want this empty listing. Or maybe we should have, well. Now, there are some multiplicities we have here. So we have this one sick list. We could delete this and then try to add a fact where we are basically saying the same thing. We could say one list because we can also use these multiplicities on any set and state them as a proposition. We can basically say we want only one list to exist. Now we get the same thing. We can only have one list thing, but in terms of performance, it's a bit more, a bit more expensive. So how would we do the lone? Let's say we don't want this multiplicity for the header node. Then we can also try to do this, but we would have to maybe say for all L in list, we want to ensure that L dot header, well, that there's 0 or 1, right? So we could write lone L header. Then we can do the same thing here for the node. So many of the multiplicities, we can actually express them in multiple ways. So for all n in node, we want to say that n dot link is, well, 0 or 1. And then we should, no, that didn't work. Why did it not work? Not sure what scopes were in here. Let's just make sure we put parentheses. No instance find. So for all n in node, 0 or 1 links, right? And without this, it worked or not? Already. For all L list. Maybe we need a multiplicity here. Okay. Yeah, so I'm not sure. The default might be what might be the default? I don't know. That's something to figure out what the default multiplicity is. But then we can basically add we could say it's unrestricted, it's set, and then we can restrict them down here. But I guess that again, this will take some toll on performance. Well, we'll see. Yeah, so you can basically sometimes implement the multiplicities using using those built-in multiplicity keywords, and sometimes you can implement them using the facts. So yeah. What we decided first was, well, we have this list, the node, then we defined the signature. Then for header, we needed to find some multiplicity. So we said, well, lone is a good one. For link, the same. We also decided for lone. And then we came up with this one list where we said, well, there'll always be one list. Otherwise, our scenario gets a bit more complicated to define this. To define the absence of cycles, this acyclic predicate. This one list, actually, we could also represent it with a different way of writing this constraint. So we can also count elements in a set by using this hash, which is basically give me the number of elements in list, and then we can compare it to integers, but that gets a bit tricky. We will see why integers in Alloy are a bit tricky, because Alloy has to translate everything to a SAT solver, and then it doesn't have real integers. It has to encode the integers basically using something called bit blasting. So basically everything that has multiple bits, you cut it down to individual bits, and then you have to write constraints on those bits. And this might lead to overflows or underflows, because representing numbers in bits is always tricky. Okay. Then we saw, we have those binary relations, and we also set the multiplicity to lone. So in general, you always think, what are the kind of objects that you want to model? So in our class example, we had the assignments, the persons, the professors, and the students. Then we need to check, is there any hierarchical relationships? So do we need to have any classes? Do we need to have any extents relations or any abstract signatures? And then we can also check what's the scope, how many of these objects should we allow, and what are the multiplicities that we should put for each of the fields and signatures. And then for the relations, again, multiplicities are quite important. How do they relate? Now that we have these relations, they're actually quite powerful. So we can express many things with relations. We saw that we can express already these things, that a relation combined with a list leads to an empty one. So we could use something like navigation, navigating from the list to the header. But we will see that it's actually a bit more, let's say, basic what we can do with these. So it's not really navigation like you would have in UML. It's all boiling down to something in our logic. So our logic is based on relations, and then everything will be a relation. We can define predicates, which are kind of named formulas that we can then invoke elsewhere. Usually we invoke them in the run command, but you can also combine predicates. So you can have maybe conjunctions over predicates. You can use them in facts. You can use them in any kind of places. The important thing is they will either be true or false, but there is not really a true or false statement in Alloy because it's a relational logic that doesn't have those true and false constants. But that's just, yeah, we will see that we don't really need them. We can work with negation of something that is true, but we cannot really say equals false because false doesn't exist as true doesn't exist. There are some tricks to get them, but yeah, we're not really looking into this. And then there might be functions, but we will look at that really in the end. Functions are things that we can give it arguments and it will return a value, which is not Boolean. So formulas formulas always give Boolean values, and then we can wrap them in predicates. So predicates always return true or false, whereas these functions, they don't. Okay, and usually when we model behavior, we want to look at those predicates and functions to see what is actually being modeled, right? So it's about not only writing the specification, but also reading the specification. And often this is not so simple, as you have seen with the encoding in the other languages as well. Do you think that the other languages are very readable? So for example, the Limbul language, the SAT formulas you encoded, what was the largest one that you manually encoded? We only had very, very small SAT problems, right? We had one example here in the lecture where we encoded this houses example in Boolean variables, right? This was already getting quite ugly. And did anyone look at the Boolean or the propositional representation of the feature models that you generated? Did you actually read the code that you generated? In this assignment 2, where you created the input for Limbool by creating the formulas for the feature model. Did you look at those formulas? Did you read them? Did they make sense? Were they easy to read? Yes? Okay. What about the SMT encodings that you did? Were they easy to read? You always have these asserts, right? So for the computer configuration, is it easy to see what the specification does when you read it? Yeah. Okay. Then they were maybe all too small. Because usually with larger specs, it gets more difficult. And also with Alloy, one of the reasons why hopefully it's a bit simpler to read is because they have these high-level language elements, right? You can have stuff like signatures and relations defined in the signatures where they belong. If you try to do that in SMT, then you kind of define them in multiple different places, right? You might define data types, and you might define functions or relations over those data types. So hopefully Alloy is a bit more readable than, let's say, the SMT code. But in general, of course, small specifications are always more readable than larger ones. Yeah. Okay. Yeah, and so basically here the English sentence that we wanted to encode was either the list is empty or some node in the list has an empty link relation. Well, actually we wanted to encode that it doesn't have cycles, but then we had to think, okay, what does it mean to have not have a cycle? So if you would translate this one into plain English, you would say something like this: either the list is empty, like no list header, or so let's step through this. So you have this either or, so you have this or relation, or, and then some other stuff, which is a bit more complicated. So the first thing we need are these Boolean operators, right? And those are like the logical propositional logic operators that we had before. Not is negation. You can write either the exclamation mark or the not. Then and we can have the conjunction with double double ampersand symbols or the end, yeah, and so on. So these are, well, quite straightforward. Then these are the normal truth tables that we saw before. So they are exactly the same as in the proposition logic lecture, which was our chapter 1, right? So nothing changed here. The only thing that changed is that we can use these operators now on more complex formulas. But we could already do that with SMT, right? We already had those to combine them with SMT, which was also more complex. Then if we want to say stuff like the list is empty, we have to have this kind of navigation and the no. So actually the no should also be highlighted, because this no basically means this is an empty set, right? So now this navigation, we said it's navigation because it kind of looks like navigation. I take one thing, I navigate to the next thing. But actually, it's called a relational join. And that's done by this dot operator, which joins stuff. So if you ever had a database lecture, then there are some like relational algebras where you have this join operator. And that's basically in SQL, you have joins on tables and you join them on common elements and you can join them left and right. So here we're basically doing a join of those two sets. Now this set has tuples of size 1. This has tuples of size 2, right? And we join them on everything that is common. So everything that is common is going to be, well, kind of pulled together, and we only preserve what is left. So if they have a common element, then we preserve the remainder of the tuple in this kind of join. So here what is left is this n0. The common elements, they will basically be removed. And it also only works by taking the ones that are directly next to each other in this relation. So we couldn't write L like list dot and then join it with this thing. This would be the join on the other side. We would have to write this differently. So this is the join that joins the most well close together elements in the two relations, and then a set is also a relation. Just that the tuples in there only have size 1, each of them. Okay, so here are some further examples. So it's again, the result of the join is again a relation where all the combinations of tuples are taken and then the common ones are basically removed, but we only preserve the ones where they basically exist. So here, if we join this A, B with the A, C, D, so now it's just a join on tuples, then we see B and A, they are not compatible. So the result would not be defined. But here, if we join AB with this B, C, D, then we say, well, the B's are compatible. So let's just join them by like contracting these B's, and then what's left is this A, C, D. So in Alloy, if you try to join something like this, it would simply be the empty set. Now we can try to join more complex things. So this is our model where we have the list. So we have one element in the list. We have 3 node elements, and then we have the header to be, well, this L0 and 1. And then we can try to join stuff. So if we join list.header, then we take this L1 with this tuple. This also starts with L1, right? So list.header, we would have L1 in common. So this means we contract this L1 and leave the N0. So the result of list.header is this N0. Now, if we go from the list to the header and then to the link, now we basically do this same thing one by one. So we first join the list and the header, which gives us this N1. Now we have this N1. and we join it with a link. Now with this tuple, n1, n0, not compatible, not the same element. So empty, we just empty this. But this n1, where was it? Well, yeah, this. Sorry, the header was n0. No, that's so we preserve this. Actually, the header list.header was this n0, and here we have the n0 and 1. So this means we contract this n0 out and preserve the n1. That's this element here. But then we have to do this join with every possible combination of tuples in the set. So we also have to try to join this n0 from the list header with this n1, n2. And this, again, it's not the same element, n0, n1. So simply empty result. That's here. Yeah, okay. So that's basically the join operation. Then here, if we just say, well, list.header, that's the same as this thing. And actually, in Alloy, singleton sets, so sets with a single element, are always considered as, you can write them as the element as well. But yeah, that basically doesn't matter whether you write the set n0 or whether you just write n0. So that's, in Alloy, it treats it the same. And then, of course, here the link that's just expanded. This only gives us this n1 from here. That's what we just looked at. Now, if we do the application of link again, we have to check what did we get after we joined the first part. So list header link, we got the n1. Now we join n1 again with link. We join n1 again with this. This one doesn't give any result. This one gives the result n2. So that's why here we would have the n2. So this way we could basically jump through or take the steps through the list. Yeah, and then we can say, well, we want this thing to be empty. In our example that we just had, it was not empty because it had here the result of list header was this n1. So this was not empty. So here we would not have the case of the empty one. But of course, we could have the case of the empty one. Okay. So yeah, these would be the set sizes. So what we said were multiplicities for signatures and for fields. We can use them again as stating set sizes. So we could say no list header means that the set is basically empty, or the size of the set is 0. In this particular example, right? Because we can imagine that there are some where list header is empty. So for example, if yeah, we wouldn't have any tuple in here, then joining the set list with an empty relation makes it empty because there's no corresponding tuple that we could preserve. So joining everything with an empty relation makes it empty. Okay, yeah, then let's maybe, I think we are out of time for today, so we will have a look back at this in the next session. In the next session, we will look at measuring the size by using this number operator and some other operations on relations and signatures. Okay, any questions right now? Or okay, great. Then see you on Friday. Yeah, on Friday we will actually have the exercise again. So yeah, see you on Friday.